Here is the failure nobody wants you about. The loop ran, it terminated cleanly, CI was green, and the agent had deleted the failing tests. Not a crash, not a hung process, not a $47,000 API bill. Just a loop that worked perfectly and delivered wrong. That's the loop engineering problem in one sentence. You can build a loop that runs flawlessly and still fails by design. The loop code is 6 lines. While goal not met, call the model, run the tool, observe the result, repeat. You can write it in 10 minutes. The engineering around the loop, exit criteria, durable state, topology, that's what determines whether you are deploying or demoing. So that's what we're going to fix today. 3 design decisions you make before your agent ever runs. Get them right, you get a loop you actually can ship. Get them wrong, you get a loop that quietly destroys something important and passes every check you put in front of it. Let's get into it. You have seen pieces of this before. The iteration cap and the stall detector showed up last time as individual guardrails. Here is how they compose into a full stack with a goal signal on top and synchronous enforcement underneath. 4 layers stacked in order. Layer 1, goal signal. The agent calls a structured done function. Small agents does this cleanly with final answer function. And that function call is the termination event, not a text pattern you are passing out of a completion. An unambiguous structured signal. This is the happy path. Layer 2, hard iteration cap. The circuit breaker you already know. 50 steps or 100, pick a number and enforce it. Won't guarantee a finished result, but it stops the runway. The missing piece in that $47,000 incident. Layer 3, token budget with synchronous enforcement. And here is the distinction that matters. Monitoring fires after you have already spent the tokens. Enforcement intercepts the call before it goes out. Your budget check has to be synchronous. Check the projected cost before you make the call, not after. Async monitoring is not a budget control, it's post-mortem tool. Layer 4, no progress detection. The stall detector, same idea as before. Hash, tool name, results preview. Each iteration. 3 matches in a row means the agent's stuck calling the same tool for the same result. Kill it before it burns the rest of the iteration cap doing nothing. 2 out of 4 is not enough. The $47,000 incident had 0 out of 4. So the goal signal layer assumes you have a goal condition that's actually correct. This is harder than it sounds. The rule, exit conditions must be binary and deterministic, not improve the UX. That's a direction, not a condition. Not make CI green, because an agent that deletes failing tests makes CI green. The test deletion anti-pattern is documented. It's not a bug in the agent, it's a design failure in the exit condition. The spec said green CI, the agent delivered green CI. The fix, the test suite is read-only. The agent cannot modify it. That's not a prompt instruction, that's a file system permission. Don't rely on the model's judgment about which files are off limits. For non-code tasks, you need a verifier, a separate lightweight model call that checks output against a rubric. Not an LLM judge scoring 1 to 10. That's too fuzzy. A classifier. Does the output satisfy constraint A? Yes or no. Does it satisfy constraint B? Yes or no. You exit only when all constraints pass. The rule of thumb. If a human engineer couldn't evaluate the exit condition in under 5 seconds, it's too vague to run automatically. Your loop's working state. Tool call history, partial results, current plan position, lives in RAM. RAM is ephemeral. For a 30-second loop, that's fine. For a 25-hour loop, OpenAI's Codex ran for 25 hours. 13 million tokens, 30,000 lines of code. Losing RAM state is catastrophic. But here is the insight that longer context windows don't solve. Long horizon coherence doesn't come from fitting everything in one context. It comes from writing spec, plan, constraints, and status to files the agent revisits each iteration. Fresh context window per iteration. File system as persistent state. The agent reads its own spec at the top of every loop. That's what lets a loop run for hours without drifting. 2 kinds of state to checkpoint. The objective, what the agent is trying to accomplish, goes to durable storage before the loop starts and is read-only during the run. Markdown files work great. The progress state, tool call history, intermediate results, where in the plan you are, gets checkpointed at every meaningful step. LangGraph implements this with a prequel model. At every node transition, state gets written to a persistent store. SQLite for local, Postgres or Redis for production is fine. Process dies at step 23 out of 50, you resume from step 23, and you can load any checkpoint, modify state, and fork execution from that point. That's your debugging primitive for multi-hour runs. One footnote: make your tool calls idempotent. Absurd semantics. Idempotency keys or a checkpoint replay creates that database record twice instead of resuming cleanly. Not all loops are linear. Topology is a design choice you make before writing the first prompt. Sequential is react. Reason, act, observe, repeat. Each step depends on the last. Simple, debuggable, write when your work is genuinely serial. Code that compiles, then tests, then lints. The cost is latency. You can't go faster than your slowest step. That's acceptable when steps aren't independent. Fan out is what LLM compiler does. It builds a dependency DAG, a graph of which tool calls have no shared state mutations, and dispatches the independent nodes in parallel. On benchmark tasks, 3.7 times latency reduction, 6.7 times cost reduction over sequential react. The constraint is strict. You can only parallelize steps with no shared state mutations. If step A and B both write to the same file, running them in parallel gives you a race condition. Do the dependency analysis first. One missed dependency in a parallel branch is genuinely hard to debug. Event-driven is least common but often the most efficient. The loop sleeps waiting for an external signal. A webhook, a file change, a queue message, wakes, processes, sleeps again. Token cost is near zero at idle. This is the right shape for any loop that's waiting on the world. Monitoring pipelines, reactive workflows, trigger-based systems. Don't build a polling loop with a sleep statement. Use a message queue. The heuristic: default to sequential until you have a measured latency problem. Premature parallelization adds coordination complexity without a clear win. Optimize when you have a number that tells you to. Let me add the one thing most tutorials skip. Most production AI doesn't use autonomous loops at all. It uses workflows, deterministic pipelines with LLM calls at the decision nodes. If your task has a known structure and a predictable success surface, a workflow is cheaper, faster to debug, and easier to monitor. The decision rule for loops: use one when the task's path is genuinely unknown until runtime, and when the failure cost of a wrong step is recoverable. And there is a failure mode invisible to every metric you have. It's a risk seen in experiments like CarPath auto research. Agents hitting hard optimization challenges default to small, safe tweaks instead of real architectural moves. The loop ran, terminated cleanly, looked healthy, delivered marginal gains. No alarm, no token spike, call it conservative drift. The agent optimizing for looking done over being done, and standard monitoring won't catch it. The deeper shift, the one that separates practitioners from hobbyists, is this: loop engineering isn't about building better infrastructure around your prompts. It's about moving up an abstraction layer. You are no longer writing prompts. You are writing programs that write prompts. Developers who master the plumbing without internalizing this build fragile, over-assembled loops that solve the wrong problem at high cost. Alright, the frame. A well-engineered loop is a contract with three clauses. Clause 1, exit criteria. Binary, deterministic, ungameable. A goal signal for the happy path. A hard iteration cap, a synchronous token budget, and no progress detection as the safety net. If your exit condition can be satisfied by an agent gaming the metric, deleting tests, reporting false progress, rewrite it. Clause 2, state durability. Objective return to durable storage before the run, read only during. Progress checkpointed at every meaningful step. Tool calls idempotent. The loop survives process death and resumes without corrupting state. Clause 3, topology. Sequential for dependent steps, fan out for parallelizable subtasks. After you have built the dependency graph. Event driven for reactive workloads. You pick the topology before writing the first prompts, not after the loop starts behaving unexpectedly. A loop missing any one clause is a loop you are demoing, not deploying. The code is 6 lines. The engineering is the contract. That's loop engineering. If you want the failure modes these patterns protect against: context blow up, tool sprawl, runaway cost, this video covers all of that. Next up, multi-agent orchestration. What actually happens when you put multiple loops in a room and need them to coordinate? Spoiler, they feel like organizations, not like programs. Subscribe so you don't miss it. See you in the next one.